we had this number up there. If I used a 1 meter stick to obtain that measurement, what would I need to change about how I've reported it? If I used a 1 meter stick to take that measurement.
You would just make a lot of measurements.
How many sig figs is that? One, 6, 4, 6, and 3. This 0 is significant because it's bound by numbers. So we'd have 4 sig figs. And all of these zeros would be placeholders and so not significant digits. As Christian was suggesting, those should all be significant digit zeros because of how I described the measurement. The measurement was using a 1 meter stick, which means to get this 0, I knew I exactly hit that line. So as it's written, it is unclear that that's the device I used. How do I change that number to accurately reflect that I used a 1 meter stick?
Put a dot.
Put a dot. There's a dot. Add a decimal point. Whoop, that I then promptly erased. Add a decimal point at the end. As soon as we add the decimal point, now the rule changes and it doesn't have to be bound on both sides. It just has to be bound to the left. That is significant, which makes all of our zeros significant. Now every single one would be significant, yes? Okay, so cool. That simple decimal point now adds clarity to how I measured that using a 1 meter stick. Yeah? Okay. So now we want to change this up and make it a little bit more difficult. How do I report this number if instead of using a 1 meter stick, and this is going to sound a bit cumbersome, but I used a 1,000 meter stick? Just assume I can do that. Okay. So the smallest marking I can go to is 1,000 meters. Are all of those zeros significant? Which zero is significant? Go 1, 2, 3, 4, 5. Which of those zeros is significant? 1 and 2 become significant because I'm using a 1,000 meter stick. That's where my precision ends, is at that line. So those zeros are now significant, and those other zeros, 3, 4, and 5, are now insignificant. Okay, or not sig figs. How do I report that measurement? We'll just do it like that. That's a lot of colors and lines. How do I report that measurement so that it accurately shows those zeros as significant? I need to be able to differentiate these zeros from these zeros. Could I put in a decimal point? If I put that decimal point, then the blue ones are significant, right? So maybe I shouldn't put the decimal point there. I'll put it over here.
No, because now it's saying a different number.
Now it's saying a different number. So I can't place the decimal point there because now that changes the meaning. Instead of it being, what was it, 400 million, I'm now 406,000. That's a pretty significant difference. So I can't put the decimal point there. How can I report this so that those numbers align correctly? If I don't specify a decimal point, those red zeros with the arrow, maybe we should call them orange zeros. Can you tell that those are orange? Sure. Those orange zeros, if I don't specify a decimal point, I don't know are significant digits. There'd be nothing to distinguish them from the blue ones. What I have to do is change how I present the number. Okay? One of the suggestions was to go for scientific notation. 4, so I put my first significant digit, the 4, into the ones place, followed by 0, 6, 3, and then I heard someone say it, 0, 0. Those zeros are now significant in this writing. I don't include the next zeros, because if I include the next zeros, that they would then become significant, yeah? Okay? But 4 versus 400 million, kind of a loss in meaning, right? So what do I need to add? 8 times 10, okay, doing a power. This is where I do have that implied decimal, and I am shifting it from 1, did I count that right? 2, 3, 4, 5, 6, 7, 8 places. Make sense? Is my number really big or really small? In comparison to what? To 1. Is that number 406 million big or small in comparison to 1? It's big, which means that 8 needs to be positive. Now I'm able to differentiate the zeros as being significant versus insignificant. There's the utility of scientific notation. It allows me to differentiate zeros as placeholders versus significant digits because I can just delete the insignificant digits. That's one of the reasons why we would use scientific notation. Yep, this was just kind of a random just example. We're trying to show that line on where it differentiates. So
Depends on the units that you're given.
it doesn't necessarily depend on the units that you're given, because do we actually address meters? We just said I used a 1,000 meter stick. Did it have to be meters? Okay, it could have been grams. Could have been liters. It could have been seconds. Okay, it could have been express that number to 3 significant digits. For it to be 3 significant digits, those can be my only significant digits. What do we think?
Actually, none of them, it's pluses, 3.
I'll get to that. Everybody get an idea? If we're going to 3 significant digits, do all of those have 3 sig figs? I just remembered another number I could throw in there. Do all of those have 3 sig figs? No. The first one has 1. Therefore, it's wrong. Last one has 1. Therefore, wrong. Do the other numbers have 3 significant digits? Yes, all 3 of those have 3 sig figs. Is 20 the same as 2,000? No, which means it's wrong. Okay. Is 2 the same as 2,000? 2 times a power of 10 could be similar to it. Notice that we have a 3 and a negative 3. Okay, so you'd have to know which way you have to shift your decimal, being it big or small, being positive or negative. Okay, in this case, it has to be positive, which means our answer becomes C. There was a statement. It doesn't say positive, so it is wrong. I would love to say that we are absolute all the time and we have to specify all that information 100% of the time, but that's not true. Okay? That positive becomes implied because I did not write minus. Okay? So positives can be implied. Negatives we can't. This is why when we look at customer service, what do we look at? All the negative evaluations. We never see the positive ones. Okay? Kind of make sense? Okay. That question should look familiar to anybody that has started the practice exam. The only reason I pulled that off is because someone had it open in the tutoring center. Okay? So, how do we measure really big and really small? So one option is showing all of those significant digits using powers of 10 and all that fun stuff. Okay? There are other ways to go through and do it because that's a lot of work. We could change the unit. We can change the core unit by adding a prefix. That prefix changes the value. So that when I talk about a gigabyte, it goes, oh, gigabyte's really big. How big is it? 10 to the 9th, okay, or 1,000,000 bytes, okay? Why did we not just reference it as 1,000,000 bytes? Which sounds cooler, 1,000,000 or giga? Those of you being like, I don't really know. It's a giga, I'm telling you. That's why we switched to gigabytes. Okay? So we invented these prefixes so that we don't have to report out all of that extra information. Okay? So these prefixes can change that so that when I'm looking at that number in meters, that's a really big number. Remember I said I used a what stick? 1,000 meter stick, also known as a kilometer. So we could have written that as 406.33 kilometers. We can change the unit to help us still convey that same meaning, but get rid of some of those unnecessary zeros. Decimal point. Okay? So let's take a look at some quick examples of this. Actually, before we do that, should we memorize all of those? Yeah, let's memorize all. No, never say yes to memorizing everything. It's a waste of time. Okay? Are you really going to deal with something at the tera level in a chemistry class? How many of you are going to measure out a teragram? Okay? You should rightfully be laughing. That's a really big mass. We're not going to do that. Okay? So most of the numbers on this, these prefixes, are now either so large or too small that we won't deal with typically. So it's not worth you memorizing. What should you do with it? You should know where to look them up. Okay? You need to know that information on where to find that information. Sometimes, though, we'll do conversions so often that what do we need to do? We need to memorize it. So which of those do you think we use so often that we should memorize? Centi, milli, and kilo. Okay, are our most common ones to memorize. So I expect you to have memorized that K means kilo, and it means 10 to the third. Okay? Centi means C and 10 to the minus 2. Milli means M and 10 to the minus 3. Yeah? Those three you should have memorized so that you don't waste time looking them up. That's when you memorize. Okay, to speed your process. Not to just memorize random crap. Okay? So, because you've now got those memorized, because, it only takes like 5 seconds, right? We should be able to apply that knowledge. That was a joke, for the record. All right, so how do we apply this? The first thing we could try and do is take a measurement and convert it into scientific notation. So that first measurement I want to convert to scientific notation will be 1.2 times 10 to the 1, 2, 3. I shifted it 3 places. Should that be positive? Is that a large number? Yep, so that's positive. And then meters. What did I say 10 to the third was? Thank you. 10 to the third was kilo. My number becomes 1.2 kilometers. Ta-da! Do the next 3. Say yeah. No? Should I stop? Stop. Okay. Okay. So if we go through and look at it, I started to scroll a bunch of answers in there. Let's take a look at the second one. Is our starting number larger or smaller than 1? Smaller, which means the power of 10 is negative. Number 3. Smaller, so 4. Smaller, so negative. What is 10 to the minus 2? C for centi. The next one is also a C for centi. And the last one is M for milli. So we get 1.2 centiseconds. Does that sound weird? Yeah, you're like, who would ever use that? Doesn't matter. We can still do it. Okay? 1.2 centiliters, 1.2 milligrams. Okay, that's how our prefixes work. It's to help simplify out some of those powers of 10. We may decide that we don't like the centisecond unit, and we may switch to a millisecond unit. That is fine. Okay? Ultimately, that is a decision that you would make as somebody reporting your answer. Make sense? Yeah? Cool. So, we're going to go back to our sheet necessarily, but this is going to jump back through chapter 3, most of which I think you've read and will hopefully all make sense. We'll see how it goes. Okay. We get physical and chemical properties. Physical properties, you don't change the substance. So the substance stays the same. We may still see some changes, but the substance at the heart of it stays the same. So for instance, if I take a block of ice and left it on the counter, what happens to it? It melts. It phase changes. Are the properties of a solid the same as the properties of a liquid? No. Okay, so one of the things we have to be careful of is being like, well, what happened to it? Does that mean it changed chemical properties? No. It's still the same substance. It just changed its phase. So phase changes are physical properties, not chemical. Okay? That does become questionable, and we'll see that in a little bit too. Okay? Chemical properties describe how that compound changes its observable properties when it interacts with something else, and so it changes its structure. Okay? Changes that bonding nature. Because we've talked about bonds, we now have an ability to understand chemical properties a little bit better. Okay? Physical properties are absolutes, so I can measure a physical property easily. Chemical properties aren't really absolutes. Okay, so I have a problem with chemical properties, because the whole point of a chemical property is that what? Change the bonds. So physical properties are absolutes. I can contact them at virtually any point. Chemical properties aren't an absolute. They're associated with a change. So it is better to think about our physical and chemical systems not as properties, but as changes. Okay, so in a physical change, it stays the same compound. Melting ice or boiling water are good examples, okay, because it's still H2O, it's just in a different phase. Okay? When we go to the chemical change, we're changing that composition. I could take hydrogen gas and oxygen gas, and I can mix them with each other. If I now light a match, what happens? So number one, boom. And number two, what happened to the hydrogen and oxygen gases? They change to become water. Okay, so it's the creation of water when those two substances react. Since we've changed the bonds, we're looking at a chemical change. So a new substance is formed. Okay? If we did this as a big kaboom, it's all probably a gas. So that means I started with one clear gas, another clear gas. I reacted them to make a third clear gas because it's hot. Kaboom, right? How would I know a chemical change has happened? Okay? That explosion could be a tip-off that a chemical change has happened. So what we want to be considering is what are those observables that we could look at to say whether it was chemical or whether it was physical. So let's take a look at some examples. Your textbook outlines what it calls as four types of evidence. I think there's three. 1 and 2 are the same. It's just a change in phase. Okay? Either going from liquid to solid or liquid to gas are the typicals. But any change in phase is typically evidence for a chemical reaction. Okay? So if I take my pot of water and I put it on the stove and I turn on the stove, what happens to the water? That liquid water. It heats up. Keep heating it. What happens? It boils. What's happening when it's boiling? It's turning into a gas. Was that a phase change? Is that a chemical change? No. Why not? Didn't we just say gas formation was a chemical change?
I have a question. So what if it's like you put substance into the boiling water? So then it's like two different substances. put water and then you put like, I don't know, your pasta in there, is that have anything to do with the steam that's coming?
So we'll do a couple things there. If we're adding heat and adding a chemical in there, okay, it now becomes more difficult to track whether it's a chemical or a physical change. Why? We're seeing a change. Was it due to the physical process or was it due to the chemical process? You would have to be able to separate those, and ultimately that's where that becomes a lot more challenging to be able to differentiate. So I would argue at this level, don't start mixing things, keep it simple. Okay? What's driving most of this is what is causing the change. Okay? What is causing that observable? When we go from a liquid to a gas, by putting the pot on the stove, what caused that change? An endothermic reaction? What allowed the water to turn into a gas? Energy. Where did that energy come from? Where did the heat come from? From the stove that I turned on. When I supply the energy to cause that phase change, that's physical. I did it. What if I take two liquids and I mix them and I see a gas? Where did the energy come from to make the liquid turn into a gas? All I did was mix two liquids. Where did that energy come from? The chemical bonds. That's now a chemical change. So a lot of these things come from how is that change happening? Is that something that is happening because the chemicals have allowed it to happen? Or is that a change that I have initiated? Okay? So in the boiling of water, I initiated it. What if I go from liquid to solid? How do I make a liquid turn into a solid? I freeze it. Ultimately, what am I saying? I'm removing the energy. I'm removing that heat. Because I am removing that heat, that is now a physical change. But what happens if I mix two liquids and I see a solid appear? That's now chemical. That energy got removed from the individual chemicals to make a new chemical. That's why we're seeing that phase change. Right? So a lot of it is if it's an external push, that's physical. If it's internal, that's chemical. There was a hand?
Yeah, you mentioned energy when the bonds, you can extract energy when bonds are made as well as broken apart?
So dealing with energy as far as bonds can become a bit questionable depending on which system you're looking at and how that transition works, which is why ultimately I haven't put that in the slides. It did show up in your textbook in chapter 12. I'm going to say we don't want to open that can. If you would like to open that can, we can talk about it outside of class. Okay? Color change. A permanent color change is a characteristic for a chemical change. Okay? If we take a look, I've got this dropper that is dropping what color liquid? Clear liquid into a solution that is a clear liquid. When those two impact, what happens? A yellow has formed. Okay? Started with two clear things. Why did the color change? A chemical reaction. I take red food coloring and I add it to white cake frosting. What color does my white cake frosting become? Some people like red. Clearly haven't mixed red food coloring with white cake frosting before. What coloring does it make? Pink. Okay? Did I get a color change? Yes. Chemical or physical? Okay? It's purely physical. That was a dilution in color. Okay? If you wanted to get red, what do you have to do? Add a lot more red food coloring to it. Okay? One of the other characteristics that comes out for chemical versus physical is a reversibility. Physical processes are reversible, in kind of air quotes, and really easily reversible. We can always reverse a process. It just requires a lot of effort to do so. Okay? When we look at that, just because this is a neat example, mixing food dye into cake frosting is physical, which means that process should be reversible. Is it? Yes, it is. Okay? Which is a difficult thing to test because as you mix, you have to ensure that you mix and reverse mix in the exact same orientation. If you're a human with your hand, you're not going to move in the same space. Okay? Experiments have been tested to prove it with a computer-generated arm, mixing and actually the complete reverse unmixing. Okay? It is possible, and you can do it as a human. It's a little bit more challenging. Glycerin in food coloring. So get a clear cake frosting. Energy change observed. Okay? If you see energy released, okay? Well, how do we see energy? You're like, you don't see energy. What is light? Light is energy. If I mix two chemicals and they start sparking, that's light. That is energy being released. Where did that energy come from to make that light? A chemical change. Okay? So energy being released is typically a sign, okay, of a chemical reaction. If it is a release of heat specifically, we refer to that as exothermic. Exo for outside. Therm is temperature or heat. So this is outside heat. If the heat goes outside, it's exothermic. If we look at the other option, the heat could go inside. If I mix two chemicals and it gets colder, it's getting colder because the heat is flowing into the chemicals. They're absorbing that heat. That is now an endothermic reaction. Endo for inside heat.
Like charging a battery?
Charging a battery does push to these layers, yes, when you're looking at those energy changes. Okay, so light emission also counts for this as well. Okay, so there's a pretty picture of light emission. Ta-da! And heat, for that matter. Okay, let's take a look at some of these examples, and you can tell me chemical or physical. Okay, what do you think? Melting ice. Okay, why is that physical? Same substance, different phase. Okay, reversible. Dissolving sugar. It is a physical. Why is it physical? So we're hearing an aspect of reversibility. Okay, there is a reversibility to that. It's a bit challenging, but you can pull that off. What happens to the sugar molecules when you dissolve in water? It's really just a dilution. They just dissolve in water. You still have sugar molecules. Okay? Burning wood.
Chemical.
That is chemical. Okay, what is happening in that chemical process? We're taking a block of wood and we're turning it into charcoal and not oxygen, carbon dioxide. When you're burning wood, what you're turning it into is CO2. Wait, what are we doing as humans? Exhaling CO2, right? Which means
We're on fire.
we are on fire. We are literally burning wood. Okay? We are combustion engines. We are producing energy through the combustion of sugar molecules. Okay? Dissolving salt. The same as sugar. Why same as sugar?
Because you're diluting it in a sludge.
Diluting it, reversible. It's chemical. We'll come back to that. Mixing red food dye with white cake frosting. Physical. Last one. This is kind of a stepwise process, so this makes it a little bit difficult to see what's going on here. So as we're transitioning from A to E. And starting with A, we have this yellow crystal. As we move through, we're seeing that crystal turn progressively darker, more of a purple shade. Okay? What's happening in this case is that we've shined UV light on that crystal and it's changing its color. When I remove that light, what happens? Goes right back to the yellow crystal. Chemical or physical? Why? Reversible. Okay. We applied some energy. Chemical. Are there any of those you'd like to talk about? Salt. Okay. Well, dissolving salt. We're making the assumption it's water, right? What does water look like? Clear liquid. What does salt look like? Grainy, white crystal. Okay. When I add the salt to the water, what happens? It dissolves, and what do I end up with? Salt water. So a nice clear solution again, right? What happens when I do sugar? The exact same process. If sugar is physical, why is salt chemical? Salt is an ionic compound. When I hit it into water, what happens to the bond connecting the sodium ion to the chloride ion? It breaks. Dissolving salt is by definition a chemical change because you broke a chemical bond. When we look at sugar, we aren't breaking the molecule of sugar. The molecule of sugar stays the same through the entire process. It's just a question of where it's located. If it's really close to other sugar molecules, we've got a solid. If it's separated, it's the solution dissolved in water. So those of you being like, damn, that's really tricky. It is. It's actually so tricky that if you check online for the dissolving of salt, you get about half the people saying it's a chemical change and half the people saying it's a physical change. Right? And they'll go to push to all sorts of other degrees. That argument on why it's splitting half and half has to do with the perception of chemical and physical. It is either chemical or it is physical. No, it is not. Notice that we're using different colors for each of those processes, right? Why would I be doing that? It's a spectrum. At one extreme of the spectrum, it's a physical change. At one extreme, it's a chemical change. There are all sorts of processes that blur the line in between. Chemical and physical is not an absolute, it's a spectrum of change. When we look at dissolving salt, why is it so tricky? Because it falls dead in the middle of that chemical and physical process. How would we be able to distinguish whether it was chemical or physical? That's where we have to understand a whole lot more about what is happening on the chemical level. That requires deeper studying behind it, which is why I feel classifying things as chemical and physical, particularly where this first showed up, which was in which chapter? Chapter 3, very early in the semester, before you understand bonds, before you understand anything about chemicals, is stupid. Okay? I say that a lot. I would apologize, except I won't, because it's just me. Okay? So there are some things that are gray areas. Would I ask you on a test dissolving salt? This is where you're all like, yeah. He would definitely do that. Okay? Go back and look at questions. I don't. Okay? Where I ask are the black and whites. Okay? Burning of wood is very clearly a chemical reaction. Okay? Mixing red food dye with white cake frosting is very clearly a physical reaction. Could I ask the question about dissolving salt? Yes. Where and how?
What happens when you put salt into water?
I could ask the question, what's happening to the salt on a chemical level? Okay? That's a really deep question. That involves a lot of extra effort on your part. Do you think I would ask that as just a general question? It's going to be hard to ask in a multiple choice if I'm asking you to explain it. So show your work sounds like a lot of sense. Right? I would probably dump it into an extra credit question. Do you really understand the nuance of those differences? Does that make sense? Okay, there were a couple of hands. 1, 2, 3, I think. Did you have a question? Okay.
I was just going to ask, so for the dissolving salt, if it was just pure sodium that you were mixing into water instead of...
Pure sodium being mixed into water opens up a whole nother can because pure sodium in water is explosive. And that is most definitely going to be a chemical change. Okay? And that brings in a whole nother system. Are you familiar with that example? Some people said red cake or red food dye into white cake frosting made red. And there were a couple other people who were like, no, it doesn't, because they've had that experience. So asking questions about physical realities outside the class becomes a challenging thing to do because not everybody has that experience. Make sense? Yes, Brandon.
Does that represent light? The bar on top, the spectrum?
It's just representing a spectrum. That's it. Which is most apparent in our visible light spectrum. That's why I was picking it. What's happening with the bottom one? It's a neat process that I studied for a little bit and did horribly at. They made a compound that when exposed to ultraviolet light changes its bond characteristics. By changing the bonding pattern within the molecule, it has changed how it interacts with light to the point where light does not pass through it. When you remove that ultraviolet light, the thermal energy, so just energy found in room temperature, allows the molecule to revert back to its starting state. Kind of neat, huh? You ever seen photochromic lenses where they change colors in the light? That's this stuff. Okay? It's a really neat compound. You can do all sorts of fun, cool things with it, including programming, allegedly. Okay? But that's a chemical change. You would know that if you could drill down into the chemical level. If you can't do that, then you don't know.
Could be another worm can.
Go for it.
But why, if you're breaking the bonds of salt, doesn't it turn into a chlorine gas and a sodium metal and then explode?
You would have to be making some other chemical reactions happen, which it can't do in that environment. So that's pushing to other aspects. You end up forming sodium ion and chloride ion. The chloride ions can't get together to make chlorine gas, which is a chemical reaction that we'll technically look at in a little while, probably in this unit. Okay? Which gets to our equations, right? Everybody knows what's in an equation, right? Some people are already giving me the middle finger. Okay, cool. At least we're all on the same page. What do we have in a chemical equation? We have reactants. The reactants are found on the left-hand side of the arrow. What else do we have? Products on the right-hand side of the arrow. What other information is there? The coefficients. What does that coefficient, that number in front, represent? I think I started to hear someone say it. How many? Okay. How many of that thing is present? Okay. That coefficient applies to whatever that thing is. How many things are there as reactants? How do you know there's two? That operator in between separates those, which means that coefficient applies to all things found within A. Okay? We have that mathematical operator, which is now allowing us to differentiate two different things being made or mixed. At the same time, we see it show up in the product side. Does it mean the same thing? Yes? So I could say for the reactants, A produced with B? No, I couldn't, right? Because on the reactant side, that is A being mixed with B to produce C and produced D. So while it's the same symbol, it has slightly different meanings because of where it is located, be it on the reactant side or the product side. Okay? It's still an AND operator, but it has slightly different connotations associated with it. What else do you see in this? States of matter. Okay? Or phases, because that's less letters. Okay, what else? I think I heard an equals. Okay? That reaction arrow gives us our equals. Okay, which mathematically works out nicely if we're going to balance an equation. We have to make sure the parts equal the same across that. Okay, this is actually saying our reaction. Okay, our reaction occurring. Make sense? Okay. That should be review. There's a bunch of other symbols and their meanings listed out here. They're also found in the textbook, conveniently, table 7.1. You are responsible for those. I will acknowledge that there is a new phase. What is that new phase? It's a solution. Okay, that's it. It's just a solution. It is the mixture of some solute in a solvent. The solvent being the liquid phase, and our solute could be anything else, just a lower concentration of it. Okay? That could be any solution, but this is actually more important than that because it's AQ. It's not saying SOL or SOL or Solin. We have AQ. What is the AQ in direct reference to? Then people go aqueous or aqueous. You can do better than that. Aquafina, water. An aqueous solution is a reaction where that substance is dissolved in water. Okay? It is not like our other states of matter phases because aqueous by definition is not a pure substance. Okay? Because it is mixed with water. Okay. Some physical laws popped up in chapter 3. Some of these may already make sense. Conservation of mass, you can't create or destroy matter. Okay, so when you run a reaction, the mass has to be the same beginning to end. There are some reactions that it looks tricky for. Let's say a combustion reaction. I burn wood. What happened to the mass of the wood? It decreases. So it's clearly not conservation of mass, right?
It still is, it just isn't on it.
The smoke, CO2, that gas dissipates from the reaction, and because it's a gas, it's harder for us to track. So there's a lot of reactions that we're used to seeing that we would seem to think contradict conservation of mass. It's because we're typically forming a gas that we don't hold on to and control. If we did hold on to and measure them, we would find that we do get conservation of mass. Okay? How do we use this mathematically? So let's take a look at two equations down below. I was able to measure out that I started with 2 grams of hydrogen and 4 grams of oxygen. How much water was I able to produce? 6 grams. How did you know it was 6 grams? 2 plus 4 is 6. You're like, really? Yes. That is conservation of mass. That's exactly what it means. What if I started with 2 grams of hydrogen, but I ended with 10 grams of water? What's my question now? How much oxygen did I put in? 8. Everybody got it? Sounded kind of like it. Should we make it more difficult? Sure, why not? I'm going to start with 10 grams of wood, 2 grams of oxygen. How much water did I make? How much water did I make? What's the mass of water when I ran this reaction? For those of you being like, this is kind of one of those dick questions, Mike. Yes, it is. This would be a question at this point you would not be able to answer. Why not? We don't have enough information at this stage in the game. Okay? We know on the reactant side I have a total of 12 grams, which means on the product side it must be a total of 12 grams. Do I know how it was distributed between the water and the gas? No. So that question is actually impossible to answer. I would need some more information. Let's say 3 grams of gas. What's our mass of water? 9. Okay. Thought I heard none of the above. I was like, what? It's early, right? 9 grams of water. Make sense? Okay. So you have to know where those pieces are. For those people being like super advanced and dealing with moles and grams and conversions like that, that's fantastic. You can't apply any of that knowledge to this question because you don't know what any of those formulas are. Okay? If you have no idea what I just talked about, don't worry about it, because you just have to do with conservation of mass for the moment. Okay? So, what happens during a chemical change? We get law of definite composition. Compounds contain the same elements in a constant proportion by mass. Okay? When we look really old school, black and white hand-drawn portrait here, okay, all we could really do was measure out the mass of these things. We couldn't count the amount of any individual molecules or atoms. Okay? So we were dealing with masses, which meant when we go through to look at a chemical reaction, we notice the masses were the same. So that if I reacted hydrogen with oxygen to produce water, I got a constant mass ratio. Okay, why? Not conservation of mass. Why did I get a constant mass ratio for water? What is water? H2O. What are we saying when we have a constant mass ratio looking at H2O?
For every 2 hydrogen you have oxygen.
For every 2 hydrogen, you have 1 oxygen. Does that say anything about mass? No. So that's not quite right. Close, but not quite. Constant mass ratio.
For every 50 grams of water, you'll have exact hydrogen and oxygen.
If we had 50 grams of water, we would know exactly how much hydrogen and oxygen. Okay. What is that exact amount of hydrogen and oxygen? Like, there's no way I would be able to figure out the mass ratio between hydrogen and oxygen in this. 2 to 1. So hydrogen, twice the mass of oxygen? You're saying no. Why are you saying no?
Because you have to have 2 hydrogens to equal that 1 oxygen.
Wasn't that 2 to 1?
But how you said it was like there's more of like hydrogen is way more because of the single one, but it's way more, or it's the same because there's 2 of them.
Wouldn't you have to take the atomic mass of each of the elements?
Wouldn't you need to factor in something about mass and not just the number of the atoms? Yes. Where do we find the mass? Periodic table. What is the mass of hydrogen? 1, which means the mass of 2 hydrogens would be 2. Great. What is the mass of oxygen? 16. Our constant mass ratio for water is 2 to 16. Okay. Which actually is going to boil down to what? Bless you. 1 to 8. So if I had, I can't do that math in my head, but if I had that 50 gram sample of water, 1 part of that would be hydrogen, 8 parts of it would be our oxygen. That's the constant composition, our law of definite composition, okay, based off of mass. Our formulas get us to that same information, but it's based off the number of those atoms. We don't have the number of atoms yet. We're too early. Okay? Yes?
What about isotopes?
Isotopes do mess with that a little bit, but the effect of the isotope is small enough that it doesn't really mess with it too badly. That is an exceptionally good question, by the way. How do we measure this? Don't stress necessarily about this, but we can figure out these masses through certain reactions. For instance, potassium perchlorate, KClO4, if I heat it up, will decompose into potassium chloride and oxygen. Okay? So I can take that and I can figure out the mass ratio of the salt to the oxygen gas. Okay? So there are certain experiments that allow me to differentiate how much mass came from one element versus how much mass came from the other element. It's kind of neat. Don't stress. Okay? Dalton comes along, adds to this, and we get Dalton's theories. We have 5 theories, right? 2 of those were false. Those 2 theories being the first one says an element is composed of tiny, indivisible, indestructible particles. For the record, there is a D in indivisible. Just so you know. Okay. What theory or what experiment disproved that? Rutherford's gold foil experiment does technically disprove that because that says there's a nucleus. I would argue that's not the best answer. Thomson's the better answer because Thomson shows that electrons exist. So that's our first delineation. Okay? 2. Because I'm going to say you guys said 2 was also false. All elements are identical and have the same properties. Why is that not true? Isotopes and isotopes doesn't count as 2 answers. But I appreciate the try. I ingest sodium, I'm dead. I ingest sodium, I'm alive. Why? Sodium metal versus sodium ion. Having a different amount of electrons drastically changes chemical properties. Okay? So having the existence of charges or electrons counteracts rule 2 as well. So, chemical reaction. Let's see what we can do. Solid sodium hydride reacts with acetic acid to produce aqueous sodium acetate and hydrogen gas. What do you see?
Oh, it's an equation.
That's a chemical equation. Cool. What about that tells you it's a chemical equation? Reacts with, okay.
Plus.
Reacts with is plus. That's a good start. What else do we have?
Produces equals.
Way to make this as difficult as humanly possible. To produce is our arrow.
Right. Sodium hydrate.
Sodium hydride. Okay, there's something we can work with. What is sodium? Na. Hydride is H. And I know it's a solid, so I'll put an S. What does that react with? You could just say acetic acid. Acetic acid, cool. Which then gives you what? There should 2 pieces of information you should immediately jump over if you see acetic acid. That's harder. There's 1, aqueous, and H in front. Okay. Now that you've got that, now you can break down your acete to recognize that this is acetate because you ate too much, so you got sick. So acetate would be C2H3O2. What? You should go back to the nomenclature video and memorize the polyatomic ions I told you to memorize. That is one of them, acetate. What does this produce? Sodium, Na, followed by C2H3O2, followed by, no, aqueous, followed by R plus, H, and gas. For those of you saying 2, give me a sec. Okay. What we've now done is broken down that name into a chemical formula. For the record, this would be a chemical reaction and a word equation, which might hit home for those of you who finished lab last week, where you were asked to provide a chemical and word equation. That's what you were expected to do. Okay? So there we go. There's our equation. Before we decide that this is done, we have to make sure that our formulas were actually correct. All we've done is pulled that information down. We didn't actually ensure that everything was valid. What do I mean by valid? What is the charge on sodium? You're like, it's not listed in there. That's true, because you were told to memorize it, and you are a rock star, and you memorized it.
+1.
It's a +1. Charge for hydrogen, or rather hydride.
1 minus 1.
It's a bit trickier, but that's a -1. Is that formula correct? Okay, to produce a correct formula, our charges must cancel out. +1, -1 cancels out. Fantastic. Hydrogen in acetate is a +1. -1 is for hydride with that IDE ending. Acetate is what charge? A -1, and you knew that because you were supposed to memorize it. Okay, is that formula correct? Yes. Sodium. +1, the acetate. -1, that one's correct. Then we move to our hydrogen. Is that formula correct? No. Why is it wrong? No. Hydrogen gas is a particularly special kind of substance that when it is by itself as hydrogen gas, it is by definition diatomic. You must specify it as H2. Okay? Don't have to worry about charges on that one because that one's not an ionic compound. Because all of our charges balanced out, we now have a proper equation. Now that we have a proper equation, what could we do? Now you can balance the whole equation. Yay! What's our process for doing that? Let's not erase that. My process, right underneath the reaction arrow, I'm going to specify each and every single element. How many times does sodium show up on the left-hand side of the equation? Once. On the right? Once. Cool. Hydrogen on the left. 5 on the right. 5 times. Just so we're keeping track. There's 1, 1, 3. 1 plus 1 plus 3. I know that sounded snarky. That was not an attempt to be snarky. On the other hand, 3 and 2, still 5. Do the next element. What's our next element? Carbon. How many carbons on the left? 2 on the right. 2, so I don't have to do anything. Oxygen's on the left. 2 on the right. 2, so I don't have to do anything. Which means the equation is balanced. Yay! No? Not yay? Yay! See, there it is. Okay. We could be asked the question, what is the sum of the coefficients on the balanced equation? This would be kind of a silly question to ask that about because you didn't have to do anything as far as balancing goes. Okay. But that question, sum of the coefficients, is referring to the number in front of each of these species. Do you see a number in front? No. What is that number implied to be? 1. Because if it was a 0, it wouldn't exist as an equation. Okay, so they're implied ones. So the sum of the coefficients would be 4. Yeah? Sure. Okay, cool. So there's our equation. Remember about that hydrogen? There are some elements that are diatomic, meaning that when we see them on their own, they will be specified as a molecule. Hydrogen is one of them, followed by nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There are a variety of ways for you to memorize this because this is, unfortunately, yet another thing that you would need to memorize. Okay? Of the variety of processes, my favorite one, all the way back to high school, have no fear of ice-cold beer. Each letter corresponding to the element that represents it. Make sense? Okay. Other options. How many elements is that? That would be hydrogen, nitrogen, oxygen, or we could, count the numbers down the side. We catching up? How many is that? 7. Just seeing if you're still there. Maybe you are. We could circle all those, right? So we see them all. Yeah, what shape does that look like? That looks like a 7. How cool is that? Except how many elements did I circle? 6, oh yeah, because I forgot the one over there. Ta-da! Eh? Hi. Any ice hockey fans? It also kind of looks like a hockey stick and a puck. However you want to memorize it is up to you, but you need to know that when we talk about hydrogen, it is H2. When I talk about oxygen, it is H2. What if I just want to talk about H? What language do I have to use to say I just want to look at a hydrogen atom? Well, I don't really know. I literally just gave you the answer. How do I know I want to talk about a hydrogen atom? I say atom. Oxygen atom is what symbol? O. Fluorine gas is F2. Chlorine atom is Cl. Look for that keyword atom. If the word atom is not there, it's as a molecule, you've got to specify it as the diatomic structure. Okay? Okay, so we already looked at that one, so let's skip that one. These are the guidelines, which you all watched. Okay, if you haven't watched, you should go back and watch. Okay, because these are our rules for balancing. Okay, the whole point in balancing is to ensure that all of your pieces add up. So let's take a look at that first equation, which I know everybody's like, I already knew how to do that one. That's okay. We're going to look at a slightly different version of it. Because I will get some people looking at that equation being like, that is not balanced. Do you agree? Yeah, that's not balanced, right? I have too many oxygens on the left-hand side. Why can't I just do this? Change the number of bonds. It does change something about the equation, right? But I'm balancing. Why can't I just say there's a leftover oxygen?
Because they can't stay by themselves.
Okay. What's coming from our chemical reaction is that we're trying to balance it out perfectly. That leftover oxygen is so incredibly reactive that what does it do? It bonds to something else. What does it bond to? Another H2 to make another H2O. So while it looks like that is now a balanced system, it is generating a material that is not stable. When I'm looking at a chemical equation, it needs to show things in their stable states. Okay? How do you know it's in its stable state? Because it's written like that. Ta-da! It's stable states. Okay? So, how do I ensure that it's balanced? Start with the first element, hydrogen. How many hydrogens on the left? 2. Hydrogens on the right? 2. That's balanced. Oxygens on the left? 2. Oxygens on the right? 1. How could I balance that? Isn't that balanced, right? Can I have a half a molecule? No, so that doesn't work. Okay, so what do I need to do? Put a 2 there. Now it's balanced. Now I've changed the chemical reaction. I can't change the reaction. When balancing an equation, you can only change the coefficients, which means the number in front. So I'll put a 2 out front. Now this becomes 2, because that 2 applies to both things. This is usually where I'll get people freaking out, but I changed the hydrogen. Oh, I don't care. Finish your equation first. Figure out what elements are on both sides. Continue through the process. At this point, we've accounted for all elements, so what do? You start over. How many hydrogens on the left? Hydrogens on the right? 4. It's 4 now because there's a 2 there, and that 2 applies to it as well. Okay? To give you another idea of that representation, I have H2O. That 2 means I have a second one. How many hydrogens are in that box? 4. Make sense? How do I make sure that that's balanced? Put a 2 here. Dang it, I'm changing the numbers again. This makes life miserable and horrible. No, it's just a step along the way. incremental improvement. Okay, are your hydrogens now balanced? Yes, so what do we do? Oxygen, how many oxygens on the left? How many oxygens on the right? Is our oxygen balanced? What do we do now? You start over. Hydrogens on the left. Hydrogens on the right. Oxygens on the right. Oxygens on the left. What do you do now? You start over. Hydrogens on the right. 4. Hydrogens on the left. 4. Oxygens on the left. Oxygens underneath. On the left. 2. Now what do you do? Why are you making me do this so much, Mike? Because I'm trying to get you just a mildly little bit irritated so that you remember the freaking process and you don't stop it halfway through. You need to keep cycling through to verify and ensure that you haven't made any mistakes. That's why it's there. Just that little bit irritated. If you're way irritated and you get it right, okay. If you're way irritated and you're getting it wrong, talk to me so we can fix it. Kind of make sense? Okay. What questions could now be asked about this equation? What is the sum of the coefficients in the balanced equation? So what you are being asked to do is to look at the number written in front of every single one of these and add them all up. Almost guaranteed one of your answers is going to be 3, 4, 2, 5. Why was the 2 there as an answer choice? Because I put a 2 there. Why was it 3? There were 3 different things. Why 4? Because 2 and 2 is 4. You're like, but how would you do that? Because what did you not write in there? A 1. Do you need to write a 1? I don't know. If you do your math and get 5, no, you don't need to write a 1. If you do your math and get 4, then yes, you need to write a 1. Make sense? Okay. Notice each and every single one of your answer choices has some root in truth. Make sure you answer the question that is asked. Kind of, sort of? You ready to break the bank and see what you can do? Yeah? Because I think these ones were in the video, but I don't think I gave the answer to them. Do that one. If you got a question, raise your hand. I'll come to you. But you should be able to solve that. If you have questions about it, you can ask after class. So what I decided to go through and do, because I noticed that SO4 sulfate stayed the same on both sides of the equation. Instead of balancing sulfur and oxygen, I can balance it out as sulfate, as just SO4 as its own unit. As long as it stays its own unit through the course of the equation, I'm effectively creating a new element. Okay? It can simplify the balancing process. Nitrate, same deal, stayed the same through the reaction. I can group those terms and solve it as a unit. It will simplify my balancing. Sorry, I skipped around a little bit. So I'll start with the aluminum. On the left-hand side, I have 2. On the right-hand side, I have 1. That needs to become a 2. I do that by putting a 2 in front. I will then actually jump to sulfate. Sulfate on the left-hand side, I have 3. On the right-hand side, there's only 1. That can be tricky to see. Don't confuse that 4 as part of that number of them. So I need a 3 in front there. Barium. There's only 1. This 2 applies to the parenthetical. The barium had 1 in the formula, but that 3 applies backwards. So I need to put a 3 there. Nitrate, the next one on the list. This one gets tricky. I've got the 2, which is impossible to see now. 2 applying forwards, and the 3 applies backwards, which means the nitrates on the left is 6. I go to the right-hand side, 3 applying forwards, 2 applying backwards, and I get 6. So my nitrate's balanced. Now what do? I get to erase all of my work and do it again, and what am I going to find? Particularly because we're out of time, that it is now balanced. Okay? If you've got questions about balancing, we will still do some practice in class. Would highly encourage you to do some practice on your own.